So we're going to carry on with our discussion of OSPF and talk about multi-area OSPF. We've thrown this term area around a little bit in our discussions to this point, and before we actually jump into the lab and start configuring OSPF, it's important to know what an area is and why you'd want to have more than one of them. OSPF, like many other IGPs, EIGRP, and RIP, they just work under most circumstances. You turn them on and configure the right networks and the right autonomous system or the right OSPF process, and all the routing just kind of happens, as we saw in the EIGRP lab. However, in very large networks with OSPF or other link state protocols, you can quickly run out of router resources. Now, why would you run out of router resources? Well, every router maintains a topology map of the entire network. As a result, every router knows about every link in the network, no matter how small or how large that network might be. As the network grows, the topology table becomes very large. As you have redundant links to networks, you have more internetworks. If you've got 10 routers in a network, it's not a big deal. But if you've got 50 routers in a network, then every time a link state happens, someone unplugs a cable, someone shuts down an interface, you've got 50 routers all running the link state calculations, running that Dijkstra SPF algorithm, and you can quickly spike the CPU and the memory on all of your routers. Every time a link goes down anywhere in the network, the SPF algorithm runs on every router on the network, and with large link state databases, this requires a lot of router resources. I go back to an experience on my current day job. I implemented OSPF and made the mistake of putting the wrong network in production in the middle of the day, and the CPU on my core router at the facility I was in just spiked at 100% and stopped forwarding traffic. And that was because it had to absorb 320 some odd different routes for all of our VPN connections and figure out the shortest path to all of them. And again, there was only one path to them, but I hadn't set up areas yet, and as a result, every time one of those VPN tunnels came up, every router on the network had to run the shortest path first algorithm. Now, the answer to that is OSPF areas. With OSPF areas, you can segment the network into separate pieces. Each area is only concerned with the routers and links in that area. The routers in one area know about all the routes in the other areas, but they're all advertised as a summary from what's called the area border router. So you still have that full convergence, but a router losing a route or losing a network cable in Argentina won't affect routers in London, to use a global example. This prevents the SPF algorithm from running on every device every time something happens on the network. It still runs on every router in an area, but if you segment your network properly and configure your areas to where they don't have more than 50 or 75 routers in them, you won't really impact the rest of the network every time something happens. It lowers CPU and RAM requirements on the routers in each individual area, although the area border routers will still have a full copy of both areas' routing tables and link state databases, so those guys have to be pretty beefy. However, it does require more planning so that you don't have routers in one area that really should be in another. So we're going to do a gross oversimplification of multi-area OSPF on this next slide. If you really want to get in depth with all the various areas of OSPF, you can look it up online, obviously, or you can take the CCNP route exam. And the exam prep for the CCNP route gets a lot more in-depth with OSPF and exactly how all the areas work together and what types of routes can go in different areas and so on and so forth. At this level of CCNA, all we're really concerned about is what are areas and how do they help my network be more stable. So let's take a network that looks something like this. Now, this network is all in one big OSPF area. It would be OSPF area 0 because you're required to have it area 0 in every OSPF implementation. So basically what would happen is if this route over here, this 10.10.6.0 network, if it were to go down, not only would the link state protocol run on this router, it would run on this router all the way over here. What if this router is in New York and what if this router is in San Francisco? You don't necessarily care that a router in San Francisco knows that a link in New York happened to go down. Obviously, it's a waste of resources because this router in San Francisco has to go through at least 1, 2, 3, 4, 5 other routers to get to that subnet. Anywhere along the way, you could get the signal back to San Francisco saying this route's not available, and you don't really have to run your SPF algorithm. So we as a network engineer decide to create two areas for our network. We split the network right down the middle. Again, in this example, that's a good way of doing it. And we have area 0 and area 1. Now again, you have to have an area 0, and we'll see that when we get into the lab. When we first set up OSPF, everything is going to be in area 0, and we'll see that taking one link down on one end of the network causes SPF to run on every router on the network. So then we'll split it into two areas, area 0, area 1, like this. And that introduces us to the first of our new terminology, the area border router. The area border router, or ABR, is a router that borders two areas. Kind of straightforward there, I know. You'll notice that the area border is on the router. It's not on a particular link or interface. So this router has one or more interfaces in area 1 and one or more interfaces in area 0. This router here knows about the full link state database across both areas, but those link state advertisements between areas stop at this area border router. The next term we'll learn is ASBR. An ASBR is an autonomous system border router. And that's this router over here. It has one interface in area 0, and the other interface could be the internet, or could be a BGP or an EIGRP network. You can think of all of OSPF as one autonomous system and all of everything else as another autonomous system, and this is the router that borders them. Most often, this ASBR will be running some type of route redistribution between the two autonomous systems. And the last term we're going to learn is the backbone area. That refers to area 0, because area 0 is normally the backbone of the network. Another term you'll run across in the exam is an internal router. An internal router is a router where all the interfaces are in the same area. These three routers are internal routers for area 0. These three routers are internal routers for area 1. So now that we've gone through all that, what does our network look like from area 1's perspective after you've segmented it off from area 0? It looks kind of like this. Area 1 knows about all of the routes in area 0, but it just knows to get the information to this area border router, and this area border router can get it where it needs to go. These routes in area 0 appear in area 1's routing table, but if this router were to go away, the only thing that area 1 would see is, I can't get to that network anymore. It does not have to run the link state computation on all of these area routers to figure out the best path, because again, there's only one path. It's through this area border router. And that concludes our discussion of multi-area OSPF.